Hello. Now, continuing on with our work on normal curves, we're going to look at standard normal curves, or kind of standardized normal curves. So what have we seen with normal curves already? We've seen that we have symmetric curves and that they have a mean in the middle, and then we have our 1, 2 and 3 standard deviations out away from the mean on both sides. But we've seen that we can have different means in different situations. So if we had a mean weight, we might be dealing with 25 kilograms, and if we were dealing with a mean weight among people in a dieting group, we might have a mean weight of 50 kilograms. So we can have different means and different standard deviations in different groups. That's sensible enough. But what happens if we want to compare different groups together, or to have a general idea of how a group is behaving in relation to other groups? Well, there we standardize our normal curve, and the formula we use to do that is this one here, which is gives us what's called a standard score or a z-score. Z-score being the more common one on the exams so far. And our z-score relates back to this standardized normal curve. So in a normal curve, we set the mean, the center, to be 0, and we say we have a standard deviation of 1. So the mean plus 1 standard deviation is going to be at 1. The mean plus 2 standard deviations is going to be at 2. The mean minus 1 standard deviation is going to be 0 minus 1 is at minus 1. So you end up with a graph like this, with a histogram or a continuous histogram that looks like that. And again, we're talking about a continuous histogram, a symmetric histogram, which we often call the normal curve, and colloquially is often known as the bell curve. That's what we're working with. So this is our formula, and what it is going to do in practice is, if we are given two different sets of data, how can we compare the two sets of data? And I'm going to give you a question that demonstrates how or why we would want to compare different sets of data. So we're on page 302, and we're going to be looking at the top of the page at question 16. So page 302, question 16. The mean and standard deviation of two French papers are shown. The marks for both papers are normally distributed. So I'm dealing with a normal distribution. That's the key piece of information given to us up top. And then in the table we have, for paper 1, we have a mean of 45, standard deviation of 8. Paper 2, we have a mean of 56 and standard deviation of 12. So if we immediately think about what our shapes, our distributions are going to look like, we have a lower mean for paper 2, and there's a smaller standard deviation. So this is going to be less spread out. So if we had this drawn on a common axis, we'd have our mean here at 45, and it'd be fairly tightly packed. We'd have our graph looking like that. That would be for our paper 1. And for our paper 2, we have a higher standard deviation. Sorry, we have a higher standard deviation and a standard mean, and a higher mean. There we go. So our mean for paper 1 was 45, and our mean for paper 2 is 56, somewhere around there. I'm not trying to be terribly specific. And our standard deviation is 12. So it's more spread out than paper 1 was. So we have a more spread out graph because we have a larger standard deviation. This is paper 2. Now, you don't need to draw that picture for this particular question, but you could be asked questions where you would draw sketches like that. and you do it more accurately than I did there, but it's just to give you a feel for what our numbers mean if we drew our normal curves for them. Now let's get into the question. So anytime we get these questions, what we're going to do is write out the information that is given to us. So we're dealing with normal curves. That's our first piece of key information. And then in paper one, we have a mean of 45, standard deviation of 8, and down at the bottom it says paper 1 she scored 59 marks. So our score in the paper is X, and it's going to be 59 marks. In paper 2 we had a mean of 56, standard deviation of 12, and that's all we know at the moment. So write down your pieces of information. This is extremely important for being able to make headway in an exam style question. So we know our mean, our standard deviation, and for both of them, and we know the original score, our marks for paper 1. Now let's read the question. What was Sarah's Z-score on paper 1? We see Z-score, we know we're dealing with this formula. A version of this formula exists in the tables, but really you need to effectively know it by heart. So our Z-score, we write down our formula. Sorry, this is part 1. Write down our formula. And let's see what information we've got. I'm actually going to write that up here. So part 1, we're looking for Z-score, so we write down our formula. And then we write down what information we need. We're looking for Z-score. X is 59. It's the mark she got in her paper 1. And mu, our mean is 45. Our standard deviation for paper 1 is 8. I've written down my formula. I've written down all of the information that's going to go into it. This prevents me from making mistakes. Z is equal to 59 minus 45 all over 8. I put that into my calculator and I get 7 over 4. And in this particular case, because you're going to be using your Z-scores with your log tables next day, I want you to always write your Z-scores as decimals, not as fractions. So this is one of the rare cases where you don't really have an option. You will have to use these as decimals moving forward. Now, what does this mean if we have a Z-score of 1.75? Well, it means that we had a mean of 0, so the class mean as a Z-score would be 0, and we are 1 3/4, 1.75 standard deviations above the mean. So we're 1 3/4 standard deviations above our mean for our class. That's what it means to have a Z-score of positive 1.75. And then part 2, Sarah expected to do equally well in paper 2. What would be the best estimate of her mark in this paper? Well, if we weren't really thinking terribly carefully about this, we'd say that she'd get the same result, wouldn't we? If we are doing 2 papers and we're saying we're going to do equally well in both of them, we'd get the same percentage. But if we think more carefully about it, the average grade for the class is higher in paper 2, and the standard deviation is also higher in paper 2. So if we got 59 marks in our paper 1, that's going to put us up at a particular point in the class, but as I've drawn it here, that would actually mean that we would probably be below the mean, or sorry, very slightly above the mean in paper 2. So if we're expecting to do equally well, we'd expect to be somewhere up here. We'd expect to be 1.75 standard deviations above the mean in paper 2 as well. So her result is not going to be 59 marks. What we're going to do in order to find her result is use the z-score backwards. So what's going to be the same in both cases if she gets the same equivalent mark would be if she was 1.75 standard deviations above the mean in both classes. So this is how we can use our z-scores to compare two different groups, because the z-scores for equivalent positions in the group will be the same. So part 2, let's write down what we know. We're using the same formula again. Z is going to be the same as it was. We're having an equivalent. We want to know the equivalent grade that she would get, the equivalent number of marks she would get if she got as good in paper 2 as she did in paper 1. So this is relative to the class how well she did in paper 1, and we're saying that's going to be the same in paper 2. Our grade or marks is what we're looking for. Our mean is now 56, and our standard deviation is 12. Now we have all of our information. Let's sub in. So we're going to have 1.75 is equal to x minus 56 all over 12. Rearranging our formula, we multiply both sides by 12 and we get 21 is equal to x minus 56. Rearranging again, we get x is equal to 77%. So the equivalent grade to do equally well in terms of the class in paper 2, she would have gotten 77% if she was to get equivalently as good. Sorry, that's marks, not percent. Be careful when you're giving your answers. It tells us in the question that's marks. So 77 marks would be equivalent to 59 marks in paper 1. So to be at the equivalent level in the ranking of the class in paper 1 you get 59%, 59 marks, and in paper 2 you would get 77 marks. So that's how you can use z-scores to compare different groups together. If you find the z-score for both groups, you'd be able to look at which one was higher or lower to see relatively how you did compared to the rest of the class. So that's the idea of our z-scores, and we're going to use them a lot moving forward, so it's important that we practice these and have our heads around them.